Hi, I am David Primus and I have a small consulting company, Barlazium LLC. I have recently been intrigued with the Internet of Things, voice-controlled devices, and small, inexpensive computers. This experiment taught me a lot about the technology. This video will share what I learned with you.
Alexa, ask Pi Station.
The current weather at Dave and Carol's house is 4.1 degrees Fahrenheit, which is minus 15.5 degrees Celsius. The humidity is 89.9%. The pressure is 29.99 inches. The trend is falling fast.
Let's take a look at how this works. As you just saw, I asked my Amazon Echo to give me the weather at my house. After a few seconds, it gave me the report. First, let's check out the hardware required for this project. We start with an Echo Dot, $50 from Amazon. This is one of several new devices that use voice recognition to perform various requests. Common tasks are to read the latest news or weather, set a timer, or add to a shopping list. These devices also interact with the Internet of Things, to turn on a light, for example. I was intrigued by the possibilities, so decided to see what I could get it to do when linked to a Raspberry Pi. The Raspberry Pi is a small, inexpensive computer. About the size of a pack of cigarettes and only $35, it was designed to put computers into the hands of young people, encouraging them to learn and get excited about technology. The Raspberry Pi Foundation in the UK introduced the first model in 2012. Since then, several new versions have been released, the latest being the Raspberry Pi 3 pictured here. This effort has been wildly successful. Over 10 million units have been sold all over the world. I have a Raspberry Pi Zero, which is a stripped-down version of the Raspberry Pi. The board you are looking at costs only $5 and when attached to a power supply, a monitor, and a keyboard, functions like any other computer. Add a USB Wi-Fi dongle and it communicates with the Internet, allowing you to use a browser or send email. Using an application to communicate with the Pi over my network, I use SSH, I can view its screen and control it from any computer on my network. Therefore, I don't need a monitor or keyboard to operate it. Next, I purchased a digital sensor, in this case a BME 280 made by Bosch. At $20, this is more than the Pi Zero, but it measures 3 weather features: temperature, barometric pressure, and humidity. The actual sensor is the tiny square metal object under the letters HUM of the word humidity. It is mounted on a circuit board to allow easy connection to the Raspberry Pi. I wanted to monitor the weather outside, so I needed to build an enclosure to shade the sensor from the sun. This is called a Stevenson screen, historically built out of wood. I made mine from plastic flower pot saucers. I cut a hole in each and connected them together with all thread. A side note here, after extensive testing, it appears as if the white plastic absorbs too much heat from the sun. It turns out wood would have been a better material. I may need to do a redesign. I needed to protect the Pi Zero from rainwater, so I installed it in a waterproof case. The sensor needed to be outside the case, but protected also, so I mounted it in a piece of PVC hanging below. The ends are covered by a fine mesh made from tea bags so that if raindrops hit them, they break apart and drain at the bottom. I then suspended the whole thing inside the Stevenson screen. I put it outside and connected the Pi to power. The Pi uses Wi-Fi to communicate with my router inside, and therefore is connected to the Internet and Amazon. Now let's talk about the technology that makes all of this work. The Echo Dot waits until it hears Alexa, which wakes it up. It then waits to hear a voice command. In this case, I say Ask Pi Station, which is the invocation name for the Alexa skill I set up on the Amazon developer site. When the Echo hears something it understands, such as Ask Pi Station, it records it, then sends it via the Internet to Amazon's cloud service called Amazon Voice Services, or AVS. AVS converts the recorded speech to a command it can understand and interpret. Let's look at how this is set up at Amazon. On the developer site, I defined several things about my skill so that AVS knows what to do when it hears Ask Pi Station. On this screen, the name of the skill is Pi Station. The invocation name is also set to Pi Station. On the next screen, I set up simple intents. These are actions associated with words. Below them, you can see sample utterances, which are words used to interact with the skill. In my case, the skill is very basic and simply tells me the weather, then stops. If I wanted, I could add intents and utterances to ask specific things such as only the humidity. Running on my Pi Zero, outside in the Stevenson screen, are two programs. The first is a program written in Python, shown here. After the program is started, it sets up a server listening for requests from AVS. As you can see, it is running locally at network address 127.0.0.1, port 5000. In another process running on the Pi is ngrok. This is a bit of magic that creates a temporary secure internet address linked to the Pi server's local network address and port. In this case, it is https://863c5b0e.ngrok.io. Once I start ngrok, I leave it running and update my Amazon skill to send requests to this address. Here is the screen in which I enter the address created by ngrok. Note that a published skill, which would be available to all Echo owners, wouldn't use this method. But since this is a prototype, ngrok sets up a temporary secure tunnel through the internet to the Pi Zero. This results in AVS sending requests to the Python program running on the Pi. Let's take a brief look at this Python program. Remember, this is a server waiting for requests from Amazon Voice Services. A few things to note. The server is created by Flask Ask, which is a Python framework making Alexa skill development relatively simple. The BME 280 sensor is initiated and a few values are set. Next, a class is defined for a thread to collect the barometric pressure readings needed to determine the trend. The thread runs the function addValues just below. This thread asks the sensor for the pressure in hectopascals every 15 seconds and stores it in a Python list. Once 3 hours of readings have been collected, it stores a new reading and deletes the oldest one. @ask.launch is the Flask Ask command that is invoked when a message from AVS is received indicating the skill is starting. This runs the function intro. This function gets the temperature, the humidity, and the pressure from the BME 280 sensor. It does a few unit conversions, adjusts the raw pressure to the sea level pressure corresponding to my altitude, 7,810 feet, and calculates the pressure trend. It then converts these numbers to text and puts them in a string with the other text for the Echo to speak. The return statement sends the speech text to AVS. Also sent is text for what Amazon calls a card. The card will be displayed in the Alexa app on my mobile devices. When the program is run, a thread is created that stores pressure readings used to determine the trend. When the current weather is requested, the pressure trend is calculated by comparing the average of the 5 earliest pressure readings with the average of the 5 latest readings. The numerical difference is then converted to text for the trend: steady, rising, or falling slow or fast. Finally, the main app runs, waiting for a request from AVS. Back at Amazon Voice Services, it receives the text from the Python program running on the Pi Zero, converts it to speech, and sends it to the Echo to play. The whole process happens in a few seconds. Let's watch the whole process again.
Alexa, ask Pi Station.
The current weather at Dave and Carol's house is 4.1 degrees Fahrenheit, which is minus 15.5 degrees Celsius. The humidity is 89.9%. The pressure is 29.99 inches. The trend is falling fast.
Finally, on my iPad or iPhone, I can open the Alexa app and see a card showing the same information just reported on the Echo. And that concludes this video. Thanks for watching.